Okay, so 2.2, the limit, right? So what we saw, so recall last time, we saw that if intuitively, if in our picture, say, the limit of f of x was L as x approaches C, right, you had some picture, here is C, here is L, and your function is approaching that value, right? It's approaching that value as your inputs get close to C. Then we saw that if in our picture this happened, then given any tolerance epsilon, we could find a place, like a distance, so that f of x minus L was less than epsilon, right? So that in C minus delta, C plus delta, the difference from L was less than epsilon, right? Okay, right. This was our observation, right? Right. If the limit really was L, right? If the limit really was L, then if somebody says, "Oh, I'd like you to stay this close to L," you can find a place where all the outputs are within that distance to L, right? If somebody says, "I'd like you to stay within 0.01, say this was 0.1, and you say, "Oh, well, look, that's not so bad. If I take this radius here, then all my outputs satisfy me." And the person says, "Well, okay, what about 0.01? Can you stay within 0.01? And again, you'd be able to find a place. You'd be able to find a place on your picture where that worked, right? And no matter what distance the person gave you, you'd be able to find a place where that happened, right? And we also note that we didn't really care what happened at C itself, right? So you can find an interval. You can find an interval around C, but not necessarily containing C. Not necessarily containing C. So given any tolerance here, it turned out you could find a distance to C, right? You could find a distance to C so that if you were in that distance, if you were within that distance, then your outputs were within epsilon of L, right? Outputs f of x were within epsilon of L. Okay, so this was the key observation, that if the limit worked like this, then this would happen. Any ask questions? This is confusing enough. Taylor.
No, this is like just very general.
Yeah,
What's the C next to in the brackets?
So this means excluding C itself.
Okay.
Okay. So that if you're in C minus epsilon, C plus delta, C minus delta, C plus delta, but not necessarily at C, because we don't care what happens at C. Right? C, the value at C can be far away from L. Right? We don't care about that. Yes.
Can you show another example? Because I have it.
Sure.
To show you
Sure. We'll do an example pretty soon.
Okay, no problem.
Yeah.
Okay.
Okay. So let me write this again in a slightly different way. Okay. So given any epsilon, there is a distance delta. Given any tolerance epsilon, or you could think of this as a distance too, right? there's a distance delta so that if x minus c is less than delta, then f of x minus L is less than epsilon. Okay. I've written basically the same thing up. So what I'd like you to do is to make sure that you understand that these two are the same thing. Okay. And maybe point out that they're not exactly the same thing. Yeah, Liana.
So is your second thought just like the first thought reversed?
No, it's just exactly the same thought, I'm afraid. Yeah. Yeah. So
I'm just confused where the x minus c is coming from.
yeah, so what's x minus c in absolute value? The distance, right? So let's translate this into language, right? So that if the distance to c is less than delta, the distance of x to c is less than delta, then the distance of f of x from L is less than epsilon. Right, so given any tolerance epsilon, there exists distance delta, so that if the distance of x to c is less than delta, then the distance of f of x from L is less than epsilon. So that's not quite the same thing as I wrote over here. What's the difference? Does anyone catch the difference? I made a small mistake. I made a small mistake over here when I was trying to translate. One bonus point on the exam for the person who catches the difference. Eliza first.
Did you forget to exclude C?
Forgot to exclude C. Great. Sorry, Eliana. You probably got it too. You both can. I'll give it both to you.
I mean, she answered it, it's still not.
I can see you doing it. Not that I can read minds, but I can't read minds. Clearly, I cannot read faces. I cannot read minds, but I can see. Okay. Okay. So so we forgot to exclude C. How should we exclude C? The distance of x to c. If the distance of x to c is less than delta, how do we exclude it? Can't be 0. Great. And is greater than 0. What? Is that?
I asked if I have a point.
What? Can you have a point for that? Yes, you may. Well, the points are just piling up today. But this is the most important stuff, so rightfully so. Okay. So this right. So does everyone see this? Right. So that if the distance of x to c is less than delta, but greater than 0, so that we exclude c. To exclude c, then the distance of f of x from L is less than epsilon. Right. And so this turns out to be the definition. Right. I'll write it again. I'm just going to write it exactly the same thing. So here's the point, that this seems like some sort of observation about limits. This turns out to be the definition of limit. This turns out to be the key way, the right way to define limit. Okay, so we say, in fact, the limit of f of x is L as x approaches c if given any epsilon greater than 0, there exists a delta greater than 0, so that if the distance of x from c is less than delta and greater than 0, then the distance of f of x from L is smaller than epsilon. Okay, and this turns out to be the definition. This is the definition of the limit. Okay, and this is how you read it. This is the English version. This is the math version. There's actually more notation that people use to make this even more concise. Instead of writing given any, people use an upside down A. Instead of there exists, people use there exists A, use a backwards E. But maybe we'll just avoid using it for now. But that's typically how we write it, right? For all epsilon greater than 0, there exists delta greater than 0 such that blah, 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 blah. Right. That's normally what we write. Because it's faster. Because we use these all the time. Yeah. Okay. So I hope you're all getting some sense of why we take this to be the definition. Okay. Let me show you how you use it, and this will be the example that I promised. So, okay. So here's the example. Somebody says, show that the limit of 3x plus 2 as x approaches 4 is, well, you know what it is. What will it be? What will it be? What do you think it's going to be? 14, right? So let's show that actually is true. Okay. So here's the game, right? We want given any epsilon to find some delta so that, as before, if the distance of x from 4 is less than delta and greater than 0, then the distance of 3x plus 2 minus 14 is less than epsilon. Right? That's the game, right? That's what limit means. We need to show that if somebody gives us an epsilon, we can find, if somebody gives us an epsilon, right? Somebody gives us an epsilon, we can find a place around 4 where that epsilon is satisfied. Right? So how do we do it? And here's one way to do it, purely algebraically. Okay, so here's the scratch book. You say, well, look, here's what I'm trying to do. I'm trying to find a place where this happens, right? I want a place where this happens, right? So let's analyze that. Let's analyze that condition. Okay? So we look at it and we say, okay, well, I can actually simplify this a little bit, right, by using arithmetic. Right? So I'm just going to take that 2 and subtract 14. Okay. And then I can simplify it a little bit more. Right? How can I simplify it a little bit more? Taylor?
You can take out the 3.
You can take out the 3, right? You can factor out. You could write it like, to be sort of pedantic, you could write it like this. Right? Just to make it clear that you're pulling. If you were pulling out a -3, it would also turn into a 3. Right? Because the absolute value of the product is the same thing as the product of the absolute values. That's what we're using here. Right? You can pull out that thing. Okay. So what's that equivalent to? That's the same thing as saying that x minus 4 must be less than epsilon over 3. Right? Delta x minus 4 must be smaller than epsilon over 3. Okay, and then you say, well, look, oh, that's great. In fact, we were trying to find a place close to 4. We were trying to find a distance to 4 that would ensure that that the distance of 3x plus 2 to 14 was less than epsilon. And lo and behold, we found it, right? We found it. If x is less than, if the distance of, so we noticed, right? So we noticed, observe, right? If the distance of x to 4 is less than epsilon over 3, then, right, the distance of 3x plus 2 to 14 is less than epsilon. Right? In fact, that's the same, those are exactly the same statements. Okay? So it turned out to be easy to find. Right? If somebody, right, so then you would write it up. Just a second, Edna. So then after this, after doing the scratch work, you write it up. And writing it up is basically just writing everything backwards. Okay, so you'd say, oh, look, right, we'll write it up over here, sorry. We want to find some delta so that blah, blah, blah. Well, take delta to be epsilon over 3. Right, take delta to be epsilon over 3. Then, if x minus 4 is less than delta, which is epsilon over 3, we see that implies that 3x minus 12 is less than epsilon. But that's the same thing as saying that 3x plus 2 minus 14 is less than epsilon. Right? And so we see that this delta works. This delta, we found the delta that works. Okay. So in the case of lines, it turns out to be pretty simple. It turns out to be pretty simple. You know, you say, oh, let's look at the condition and simplify it, and that will turn into something that tells you exactly the distance you're looking for. Okay. So like somebody wanted you to stay, right? So now if you want this thing to stay within 1, if you want this thing to stay within 1 to 14, where do you have to stay? How close to 4 do you have to stay? So, right, to make 3x plus 2 stay within 1 of 14, how close, don't answer please, don't blurt it out. How close must x be to 4? Okay, so take 10 seconds and write it down. How close must x be to 4? Okay, turn to your neighbor and say what your answer is. Okay, so what's the answer? What's the answer? 1/3, right? 1/3 is the answer, right? Right, to stay, right? To ensure that, right, to ensure that 3x plus 2 stays within epsilon of 14, we need x minus 4 to be smaller than epsilon over 3. Right? The distance to 4 has to be smaller than epsilon over 3. Right? If I said, I'd like you to stay within 3 of 14, I want you to stay between 11 and 17, well, how far are you allowed to be? 1. Right? If I want you to stay within 6 units of 14, how far can you be? 2. Right? In fact, you knew this already, right? Because this is a line with slope 3. Right? This is a line with slope 3, right? So you know, so here, right, there's slope 3. So if this is 4, right? Every time you step over 1 unit, then the thing moves 3 away. Right? So every time you step over a delta unit, the thing moves 3 delta away. Right? This thing has a speed of 3. Right? So In fact, you knew this. You probably knew this. If you thought about it from that point of view, you know it already. Okay, but but I'd like you to also be able to see it purely algebraically, okay? Because last time I was sort of joking. I said I'm blind. I can't see what you're showing me. But the thing is that if you go into higher dimensions, everybody is blind, right? If you're doing this sort of stuff outside of like R1 to R1, well then maybe everybody is blind, right? Not many people can see in higher dimensions. Some people can, I think. Yeah. So I tell a story. My thesis advisor in college was one of these people who was said to be able to see in 4 dimensions, which is great. He was a great mathematician, but it's sort of like it's hard to learn from such people because you go in and you say, "So, professor, here's what I'm working on," and then he looks at you and he says, "Yes." It goes like this. You see it, don't you? So like undulates his arms a little bit. So I didn't really get much from talking to him. Yeah, because to him everything was visual. Yeah, he was a nice guy though. Okay. Yeah. Okay. So I hope everyone get back to yes.
I was just wondering.
Yes.
If they give you your tolerance, is there any point that you're going to be solving for x, or you always want to get what your limit is at?
So here's the tolerance thing, right? You're trying to figure out. Somebody says, "I'd like this to stay within this of this."
I meant your epsilon. If they give you like 0.01,
Yeah.
is there any point that you're going to be solving for x, or do you always want to get, like, for example, where you got x minus 4?
So
that's the limit?
rather you figure out, given somebody gives you a tolerance, you don't figure out where the tolerance is. You don't figure out a specific x, but you figure out a whole range of x. So like somebody says, here's your function, right? I'd like you to stay this close to the limit. And you would find a full range. You would find, like, as long as what you find is the distance to C that guarantees that the tolerance is satisfied.
Okay, so not the exact.
Not the exact x, but you find a whole bunch of x, right? You find a whole range of x, right? You find that, like, what we just did was we said, well, any x between 3 and 5 will do, right? Any x between 4 minus 1 and 4 plus 1 will do to ensure that the outputs stay between 11 and 17, right? So all these x will do. All these x will do. Okay. Sorry, I feel like I'm asleep. Yeah. Okay. Other questions? Questions? Ask questions. Or, yeah. Okay. Okay. So let's just do a quick example that you choose. Okay. So give me a line. Give a line. We want to show that the limit of as x approaches some number. What number? 2x minus 3. As x approaches what?
3.
Let's do something other than 3 just to use a different number here. Okay, so we end up with 7 numbers. Okay, so what delta will do? Okay, given some epsilon, what delta will do? Don't put it out. So, I mean, one, you can just look at it and do it, but I'd like you to go through the process. Okay. So go through this and see how the delta pops out. Okay. Okay, so take, say, 1 minute to do this. Okay. Turn to somebody next to you and tell them what you're doing, even if you haven't finished yet.
Oh, yeah. Yeah. So,
Are we-
non-pretty ones that are like quadratics and weird things.
Yeah. Let's just stick with this one. Yeah. That is, for these, for such things, there's a straightforward way of doing it.
yeah.
For other things, basically, there's no particular method. You have to think on your feet and then invent why it's true for that thing.
Great.
Yeah. It's not, I guess for quadratics there is a method. For quadratics there actually is a method. But for functions for general functions, well, you have to do it yourself with your bare hands. Okay. So what delta will do? What delta will do? Somebody gives you an epsilon. Somebody gives you an epsilon of 2. What's the delta? 1. Somebody gives you an epsilon of 1. What's the delta? 1/2. Somebody gives you an epsilon of epsilon. What's the delta? Epsilon of 2. So, right, and you figure that out by saying, well, let's look. Now, we see that if we're trying to make this less than epsilon, this is equivalent to, which is equivalent to 2x minus 5 less than epsilon, which is equivalent to this thing being smaller than epsilon over 2. So, right, take delta to be epsilon over 2. If x minus 5 is less than epsilon over 2, then 2x minus 3 minus 7 is less than epsilon. Yeah, Cynthia.
Well, this is like a general thing. So when we're solving a problem like this, you want us to write the last part. If you don't give us a specific epsilon, for example, would you want, or like even if you do, would you want us to write it just like that? Like,
Yeah, basically.
Okay.
Yeah, in fact, I should probably be, if you're being proper about it, this is sort of like the scratch work.
Yeah.
And then this is what you would show me. You would say, given epsilon greater than 0, take delta to be this. If this happens, then 2x minus 10 is less than epsilon, but that's equivalent to saying 2x minus 3 minus 7 is less than epsilon. Right, so delta equal epsilon 2 works. Actually, you don't need this last part. That's obvious. Once you get to here, obviously you've reached it. Right. And actually, to be very proper, you should probably say we want to show that given epsilon greater than 0, blah, blah, blah. So you'd sort of state the problem. You'd say we want to show given epsilon greater than 0, there exists a delta so that if blah, then blah. Well, given epsilon, take delta to be epsilon over 2. And we see that it works. The end. So that's formally how one writes. Any questions about this? So this is the limit. This is the limit. Right? This is the limit. Yeah. And this turns out to be the way that so you take your intuition about the limit, right? Where you think, oh, as you get closer and closer to C, the outputs get closer and closer to L, right? Which is certainly an idea about what the limit should be. But it's not a usable idea, particularly in higher dimensions. Right? Oh, as you get closer to here, you get closer to here. I can't see it. Right? I can't see it. But using this, you can. You can talk about limit in other contexts, in other settings. Okay, so useful properties of the limit. Okay. So first one is this, uniqueness. So we've just defined the limit in a completely different way, what seems like a completely different way from the intuitive way, right? We focused on only one aspect of it. So you might be worried, right? Is there only one limit? Is there, with our definition, is it possible that you could go into a room and come up, you and your friends could go into different rooms and come back with two different numbers that work, right? Is it possible that there are two L's that for which for all epsilon greater than 0 there exists a delta such that blah, 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 right? So is it possible that there could be two limits that work, that satisfy your definition? And the answer is no. So suppose you go into one room and you find that the limit of your function as x approaches c is L, and suppose your friend goes into another room and comes back saying that the limit is m. Well then, it will always turn out that those are the same numbers. So the limit actually is well defined. Another list of properties, which I'm going to call the main limit. No, I'm going to call it limits and arithmetic. Okay. Suppose you have one function whose limit is L as you approach a point, and you have another function, G, whose limit is M as you approach the same point. Okay, so you have two functions. One has a limit of L, one has a limit of M. Okay. Then, first off, the limit of the sum function is going to be what? As x approaches c. What do you think? The limit of the sum is going to be? Just blurt it out, anything. L plus m. Yeah, it'll be L plus m. The limit of the product function f times g is going to be L times m, Lm. The limit of the quotient, the limit of the quotient function is going to be L over m as long as n is non-zero. And the limit of one of the functions scaled by some number alpha will be that number alpha times L for any alpha, real number alpha. Okay, so all this is saying is that the limit and arithmetic, the limit interacts with arithmetic kind of as you hope it would, right? If the limit of one guy is L, the limit of the other guy is M, then the limit of the sums is going to be L plus M. Right? Another way of reading this is that the limit of the sums is the sum of the limits, right? Limit of the sums, right, is the sum of the limits of the individual guys. Sum equals sum of that. In other words, it doesn't matter what order you do it. You can take the limits first and then sum them, or you could sum them and then take the limits, right? one way may be easier than the other. Okay. Similarly, the limit of a product is the product of limits. The order doesn't matter. You can take the limit first, and then product, and then the limits. Right? Limit of the quotient, et cetera, et cetera. Okay. This last one is if you multiply the thing by some number, like 5, right? Then the limit of the multiplied guy will be 5 times the limit of the original guy. Okay. Any questions?
What about subtraction?
Subtraction? What about subtraction?
It's the same thing.
It's already in there. Yeah, it's already in there because if you multiply this guy, if your alpha is -1, then you get a negative out here, right? And then we can just put it with, we can combine this one with that one, and subtraction is included. Yeah. So mathematicians generally try to use as little chalk as possible, right? Well, that's not true actually. Well, try to make as minimal minimal of your statements as possible. So if it's already included, I'm not going to make a property 5 because it's already in there. Okay. And I should say that each of these statements actually has to be justified. You have to say, well, why does it happen from the delta epsilon-delta definition of limit? And so you have to go through some small argument. I don't think I'll do it right now, but maybe on Friday I'll show you one example of how one does it. It's actually pretty simple. But for right now, let me just show you how you use it. Okay, so here's an example. So we know that, say, the limit of x approaches c, and the limit of x as x approaches c is what? C, right? That's easy. If you want, you can go through the epsilon-delta argument. Let's just say it. Okay. So if we use now the second property, so then property 2, then implies that the limit of x times x as x approaches c is what? C squared, right? C squared. That the limit of x times x, right? X cubed is going to be c cubed as x approaches c, and et cetera, right? So you have for each monomial, you have that the limit. You can get the limit just by evaluating the monomial there. Okay. So for each of these guys, looks like all you need to do to find the limit. We don't have to run through the epsilon-delta argument. We can just say by the theorem, property 2 says that the limit of a product is the product of the limits. The end. Okay. So the theorem is a big time saver, basically. Right? Like, it's almost as if we introduced the epsilon-delta and then we said, let's never look at it again. Rather, let's use the theorem to circumvent it. Okay. Similarly, right, if I multiply one of these monomials by some scalar, right, x to the 3 as x approaches c, well, I'm just going to get that scalar times c cubed, right? Right. You also have this sort of thing, right? And then if you combine this information, this above information, so this is by property 4, we see that scaling guys, just scales the output, right? Okay. So putting all these together with property number 1 means that if we have the limit of, say, a sub n x to the n plus a n minus 1 x to the n minus 1 plus, let me call these guys alphas, sorry. Alpha 1 x plus alpha 0 as x approaches c, then what do we need to do? We just, when all these alpha guys are fixed numbers. Okay. So you have a polynomial, then what's the limit as x approaches c? Well, number 1 says the sum of the limits is going to be the limit of the sums. Right? Tet, what are you going to talk? Say it again?
I don't know if it's the same thing as the long chain.
You're gonna tell me what I should write here. The limit as x approaches c of this thing is
that same?
the same thing. Well, x is approaching c, right? So
Oh, instead of x, you put c.
instead of x, you put c. You just evaluate, right? Let me make this more complex. Sorry. Let me get back to this. So if I say something like this, limit of 5x squared plus x as x approaches c. Well, what's that going to be? It's just going to be 5c squared plus c. Why? Well, because the limit of the sums is the sum of the limits. Right? The limit of the sums is the sum of the limits, right? So I get the limit of this guy, which I just saw is going to be 5c squared, plus the limit of this guy, which we know is just c. Okay, so by property 1, right, by property 1, what we see is that polynomials can just be evaluated. Right? The limit, what we see is that if p of x is a polynomial, then the limit of p of x as x approaches c is just p evaluated at c. Right? Okay. So if somebody tells you, I'd like you to show me that as x approaches 5, x cubed plus x is 130, so, right? You don't have to give an epsilon-delta argument, right? You can just say, well, by the interaction of limits and arithmetic, I know that polynomials, the limit of a polynomial turns out to be just the polynomial evaluated at that point. Right? So that's the end. So you don't have to go through the epsilon-delta argument, which is good. Okay, let me stop there and hand back some homeworks. Remember that next time we have an exam,